I'm going to record here. So we're going to pick up from where we left off. We already talked about reflexive and symmetric. Remember, reflexive, think about a mirror. Symmetric, think about cutting your body in half. We did transitive, we talked about different heights and such, and that's kind of what we stopped. The addition postulate. All the addition postulate says is the following. If two quantities are equal, and you add another quantity to both sides, it's still the same thing. Okay? So if we each have $1, and then we each both gain 50 cents, we both have $1. Pretty straightforward. Multiplication, same idea. If you have the same quantity on both sides, and you multiply both sides by the same quantity C, it's still equal to each other. Okay? Or, yes, we can. Yeah, hit that. All right. Just hit the switch there. Oh, it is a little chilly here, too. All right. These might be a little bit different. Something like closure might be different for sure, so you might want to write that with them. The other ones are pretty straightforward. I think you've seen it before. So these are called field properties. One of your homework questions tonight is going to ask you about whether it's a closed field or whether the field properties hold true. And what that means is that all of these properties have to exist. And I'll explain this right now. So, for all real numbers we're talking about in this case, not imaginary. If, in this case, if we had the three numbers 12, 6, and 5 for A, B, and C, if you want to know if a set is closed, it means that the operation results in another member of that set. For example, 12 plus 6. What is 12 plus 6? 18, right? Isn't 18 still a real number? So the real number is, the real system, or the real set of numbers is closed under addition. No matter what, if you add any two numbers, you're going to get another number that's real, right? So think about any real number whatsoever, add it to another real number, you still get a real number. Where this is different though, think about like the natural numbers. Remember the natural numbers were 0, 1, 2, 3, and so forth? Okay. Now, for the real number set, or for the real number system, if you were to try and see if that is an operation that is closed, you would have to say that the sum of any of these two numbers must give you a third number within the set. For example, if you have so the real number system, sorry, let me rephrase this. The real number system, the natural number system is closed under addition and multiplication. Later on, when we talk about identity properties, it's going to be different. So hold off on that for 1 second. I knew I had that in my head for a reason. So the idea of closure, if you look at the, let's say you had a set of 1, 2, and 7. Say that was your set. There's only 3 elements to the set. If this were to be closed, the sum of any, under addition, the sum of any two should give you another member of the set. But if you add 1 and 2 together, what do you get? Is 3 in this set? So this would not be closed under addition. Is that clear? Again, under addition. For something to be closed means that the operation results in another member of that set. So even multiplication wouldn't be. 1 times 2 is 2. So it seems like it's closed, right? Think about it. 1 times 2, you get 2 as an answer. It's in the set. But what if you do 2 times 7? What do you get then? Is that in the set? So it's not closed under multiplication either. So closure under addition and under multiplication is the idea that an operation performed has to result in another part of that set. Okay? We'll get into the natural one in a minute as we get to know this. We all know the commutative properties. You can switch the order, that's all it means. So 5 plus 3 is 8, 3 plus 5 is 8. 5 times 3 is 15, 3 times 5 is 15. Okay? So, for multiplication and addition, it is commutative. What about division and subtraction? What about division and subtraction? Are they commutative? Why? Give me an example.
Because 5 minus 3 is 2, but 3 times 5 would be -2.
Associative. How do you remember associative law? Because I remember that when I was in school, it was a little trick to remember what the associative law was, besides memorizing it. What does the word associate mean? You group, right? Group. You're associate. So if you associate with a certain people or a certain group of people, it's how you are grouped. So it's all has to do with grouping. A and B are grouped, aren't they? And then suddenly B and C are grouped. Does it matter? No, it doesn't matter. Just like multiplication doesn't matter. A and B can be grouped and B and C can be grouped. Makes no difference. It's grouped very easily. The identity laws. What do you mean by identity?
That the numbers stay the same.
Yes, very good. Identity, like identical, right? It stays the same. So the identity element for addition is 0. Because anything plus 0 is itself, isn't it? And the identity element for multiplication is 1. Because anything times 1 is itself. You clear with that? Okay. Inverse. Additive inverse. What do you think about inverse when you think about this? It's not inversing multiplication.
It's when you add two numbers, but they kind of cancel each other out.
Very good. Absolutely. They cancel each other out. So the additive inverse is the idea that when you add a and negative a, you always get 0. Multiplicative inverse is a little bit different. Okay? We call this term reciprocals. We're all good with that? Reciprocals. Let's see, and then distributive, I hope we all know. Take the first element, oops, and multiply it by the other two. So the arrows are off, the smart word is off. Take A and multiply it by both of those, B and C. Now remember, the distributive law works whether this is plus or minus. Okay, it does not matter either one. So if a set of numbers is closed under ball field properties, like the real numbers are, an example one that is not closed was the natural numbers. The reason being, think about all of these elements in this set. You start with 0 and go all the way to infinity, right? Is there a way to have a multiplicative inverse for 0? What is the multiplicative inverse of 0? For example, if I have the number 3, right? And I want to get back to 1, and I'm multiplying, what do I multiply by? 1/3, right? But here's the problem. With the natural set, if I have 0, what do I have to multiply by to get to 1? Yeah, you can, right? It's like saying you multiply by 1/0, which is what? 1 divide. Be careful, 1 divide. Okay? 1 divide. So when you're asked, there's going to be a problem in your textbook at the end, it talks about field sets. You have to see if that set will fall into, or will hold true for all of these different rules. Okay? It'll be a little bit easier when we get through a few more examples of it. All right, let's take a look. This is a rather quick section, so we're going to fly through a little bit here. So, quickly, when you multiply 3 things that look like they're grouped separately, what's the first thing you do? What law are we going to use? Associative, commutative, which of them are we going to actually use here? Distributive, not distributive, there's no plus sign. Remember? Plus sign is the given. Associative, why associative? This is association, okay. Any more?
Because there are 2 parentheses and it doesn't matter if you switch the parentheses.
Okay, so right away you can say like, we can move these parentheses around. 14 times 3xy squared, I can put the parentheses here, right, like that instead. Then I can put the other parentheses around the full thing, good. We also use the commutative law here, because if you wanted to simplify this, wouldn't you really multiply all 3 of these numerical values first, put it on the outside, right, yielding 210? Yeah, 210. And we're going to 210x y squared w to the 4th. So whenever you're simplifying stuff, whether you realize it or not, you're using your associative laws and your commutative laws. It's just that you have to learn them and understand where they come from, and then see their applications. Very, very easy example here, I know that. But I want to give you guys an idea of why you're learning the laws. It's not just for fun. All right. Now, this is the kind of problem that you're going to see on your exam for this section. You're not going to see that basic problem a little bit ago. Here what we want to do is go through the process of solving this, or simplifying this expression, and give a reason for each step. And I think you've done this before, right? If You've probably seen this before when you take algebra 1. We have to give a reason for every step that you perform. So, we're starting with the original one here. To get to part A, which of the properties do we use? Which property do we use to get from our starting point up here to part A, and we're going successively down the line? Distributive, very good, Summer. Again, you're distributing this 2 to both terms, yielding 2y plus 2. Good, that's the first one. Now to go from A to B, of which? Very good, well done. It's a little bit trickier one, because you don't see what happened right away. All that's changed is there's a 1 here, right? And that's identity multiplication, because if you multiply by 1, it's the same thing still. So we haven't changed anything. So we have distributive, and then we have identity of multiplication. Third one. Good. Associative. Why?
Because you took you changed up the parentheses and put 2 on the outside.
Yep. All you did was change the parentheses. That's it. Took the parentheses and moved them over. Why can we do that? Because they're all being added together. Okay, we can just move them over. Part D is a little bit trickier. What's part D? What law would that be? So we have to kind of think outside the box. Possibly also associative. Why would you say that? Curious.
It was like two groups. They broke up.
Okay, I see you're seeing like a group here and a group here, kind of. Okay. It's not associative, but I understand your reason for it.
Distributed.
Yeah. It's like the undistributive, right? It's like taking the distributive law and working backwards. If you have a y in both of these terms, technically you can pull the y out front. And then the 1 plus 2 here gives you that 3, right? Now, what is the last step? So if you have to give a description for part E, which is not really needed, but if you have to give a description of how you got part E, what would you call that? How do you get from this line here down to this line here? What's the only thing that's happening? You're just adding 2 numbers together. And what are we doing with the value? We're adding these 2 together, and we're replacing it with this value 3, right? What did we call that yesterday? Was it still there? What did we call it? We added 2 values, and realized it's a new value. We're going to plug something else in for it. Yeah, substitution principle. Okay, you don't need, the last one's not really necessary, but that's the substitution principle. Okay? But again, 1 plus 2 is 3, so instead of writing it as 1 plus 2, you're plugging in 3. Okay? Questions on this? They're not going to be difficult in the sense that you're going to have to do the work yourself, but identifying and remembering the properties might be a little bit tricky. Okay? Your homework for 1-3, we're not done. We're going to go on to 1-4. But just to give you a heads up for your homework so you can see it. Your homework for 1-3 is going to be 7 through 37 odd. In addition, I want you to read page 26. I'm going to only write on the right side of the board for now, because the left side doesn't work there. It's just driving notes. So read page 26. You're going to see it's like a little thing about reading algebra and understanding the concept behind what we're going to be seeing in this book. And there's going to be like a reading on the top, and then there's going to be a bunch of questions on the bottom. You don't have to do those questions, just do the reading. Okay? So when you get to page 26, just do the little reading for it. You don't have to answer the questions at the bottom. All right. The reason I'm going on to 1-4 right away, just for a heads up, which is 1-4, 1-5, and 1-6 are all really review. So I lumped them together in my notes, and I've also done that in our PowerPoint here, or in our smart books. So, section 1-4 is about sums and differences, which you all know about already, means adding and subtracting. Section 1-5 is about products, multiplying. Section 1-6 is about quotients, or dividing. So we're going to lump them all together in 1-4 to 1-6, sums, differences, products, and quotients. Okay? Your homework from here is going to look like it's a lot, but it's really so simple. It's questions like 2a plus 3a equals what? Like simplifying that, just to see that you know that you can add like terms. So there's going to look like there's going to be a lot of problems with this homework, but trust me, you can go through them very quickly. And a lot of them you can just do up in your head. I want to go through all the laws and make sure that we're clear about that. If there's any question as I go through that, I can give you an example where it becomes, okay? So, first, for sums, if A and B are negative, so if both of them are negative, then A plus B must also be negative. And think about it logically. If you're good with this, by the way, if this makes sense as you go through it, you don't have to write everything down. If you want to just hang out and just relax, you can print out the notes later from Google. The notes is only one page, that's it. So you just want to hang out and add the page in later, you're welcome to do that. Because again, this is just review. So if A and B are both negative, you add them up, you get a negative quantity. And the easy way to think about that is this. When you add two negatives together, it's like you're adding the positives together, absolute value, the positives, and then you tack on the negative in front. So if it's negative 3 and negative 5, it's just negative 8. If A is positive and B is negative, and if A's absolute value is bigger than B's, then the sum is going to be positive. And think about this logically. If the positive number is bigger than the negative number in absolute value, then it's going to remain positive. It's like saying 9 plus negative 4. It's still going to be positive 5, right? And then vice versa. If A is positive, B is negative, but A is smaller than B in absolute value, then it will become B. That's it for sums. Any questions on sums? All seen this? We're good? All right, differences. Subtraction. This is something that you should know. I mean, it should be automatic in the back of your head. Whenever you see subtraction, think about adding odds. And it really does come into play later on. It's useful to know that when you say A minus B, it's really A plus negative B. Okay, that should be kind of up here already. So think about it. If you don't know, maybe you want to jot that one down, but it's pretty straightforward. Distributive property, a multiplication with respect to, WRT, okay? That's what that stands for. With respect to subtraction, it's also holding. So if we have this property, it's just AB minus AC. Same as what we did in a minute. Okay? All right, products. There's a good amount of rules here. The products of two positives or two negatives is still positive. 7 times 7 is 49. Negative 7 times negative 7 is still 49. Second, the product of a positive and negative is negative. You know, the absolute value of the product of two or more numbers is the product of their absolute values. Let's discuss this one. Makes sense? But let me give you an example. So if you have the absolute value of negative 3 times the absolute value of 7, it's the same thing as saying the absolute value of negative 3 times 7. And think about it. What do you get here? And then here? 21, right? Same thing. So what it's trying to say here is this. If you have absolute values around all your elements, and they're all being multiplied, you could just lump them all together and put an absolute value around the whole thing. Right? What do you have? 0? Don't know that. Anything times 0 is 0. Property. This should be a typo. Property of negative 1. Okay? Anything times a negative 1 automatically becomes a negative quantity. So whenever you have a negative quantity, you can always factor out a negative 1. And that's going to come into play when you get to polynomial functions. Because there are times when you might have a polynomial that looks like this. Okay, say we have a polynomial equation that looks like that, and we're also trying to factor it. It's a lot easier to factor stuff when there's a positive here in front. So you would just factor out a negative 1 out of everything. So you pull out a negative 1 here and write it like this. Okay? You all see that? And then the negative 1 can actually drop off, because you would divide both sides by negative 1, and it drops off on the right side. So it is useful. That's a very useful one. That should say negative 1. A product of non-zero numbers is positive if the number of negative factors is even, negative if the number of negative factors is odd. What does that mean? Can somebody give me an example of that one? Because it can seem confusing at first. It's very useful to know this. What do I mean? Let's say I have negative 2 times negative 4 times negative 3 times negative 7. Negative 2 times negative 4 times negative 3 times negative 7. What kind of an answer am I going to have? Positive or negative, right? Because what? It's an even number. That's all it's saying. And think about it. This is going to yield a positive, then it's going to go back to negative, then it's going to go back to positive. So whenever there's an even amount of negatives, it's going to be positive. But if there were an odd amount, when we stopped at 3, we added the 7, this would yield a positive, and then this would yield a negative. Okay, so whenever there's an odd amount of factors, it'll remain negative. Finally, the last one is just saying, if you have a negative on the outside, it can be distributed on the inside. It's pretty much the reverse of property of negative. Okay? Quotients. There's only a few for quotients. First, division is defined. This is a good one to know, and you should really know this actually, especially when you get to something called matrices. When you look at a matrix, you're going to have to divide by matrices, and you can't actually divide by a matrix. You multiply by the inverse of the matrix. So we're going to define division, defined as the multiplication by the reciprocal. Okay, by the reciprocal. So if you were to say, we have 7 divided by 2, it's the same thing as 7 times 1. So that's the answer. I'm saying 7, fill in the blank.
Oh, okay.
Dividing by 2 is the same thing as multiplying by. Sorry?
Wait, let's do that again.
So 7 divided by 2, I can rewrite that as 7 times some quantity and get another answer. It's the same. 0.5 or, is it a fraction? 1/2, okay? Again, division is defined as multiplication by the reciprocal, okay? Always remember that, because it's going to come up a lot this year. Obviously, note that 0 is no reciprocal. We talked about that before, so division by 0 is not defined. The quotient of 2 positives or 2 negatives is positive, same as multiplication. The quotient of a positive and a negative is negative, again, same as multiplication. The last part, very, very useful. Whenever you divide any polynomial, poly means what? More. It means more than one, sure, but like a binomial is more than one, you would call it a binomial. When I say polynomial, what do I really mean? Yeah, it's like negative. Poly means negative. So when you say polynomial, you're talking about like anything really beyond 1, but generally speaking, if there's one term, just A, or in this case just C, it's monomial. 2 terms binomial, 3 terms trinomial. After that, we really club any polynomials. There's no quadnomial or pentanomial. Now, remember that if you ever divide by a monomial, it's the same thing as dividing every term in the top by that monomial. So if you had 7 plus 3 divided by 2, what's 7 plus 3? And what's 10 divided by 2? Okay, now if I do it differently though, if I do 7 divided by 2 first, what do I get? What's 3 divided by 2? What's 3.5 and 1.5? Same answer, right? Again, whenever you're dividing something by a monomial, you can divide it into each of these individually. Okay, remember that, please. It's very important. We're going to use this a lot this year.
But wouldn't A plus B be a binomial?
A plus B is a binomial. I'm just giving you a general rule with a simple example. So in this case, if we're talking polynomial in general, it could be A plus B plus dot 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 all the way to K or whatever. So you know what I mean? It could be as many as you want. Any questions on that? Pretty straightforward, right? That's everything 1 through 4 through 1 through 6 right there. So I wasn't joking with you guys. The beginning stuff is all review. Okay? So it looks like a lot. Trust me, it's not too much. I know it looks like a lot. Okay? But it really isn't much. And let me explain what this means. Multiples of 4. Okay, so for example, for the first section, I want you to do 4, 8, 12, 16. Those are multiples of 4. 5 to 35 is just going to be 5, 10, 15, 20. And then multiples of 3. 3, 6, 9, 12, so forth. Okay? I don't think it's that much, to be honest, guys. Like, I look at it, and to do this, like one section, it'll probably take you between 5 and 10 minutes for each of these. So we're talking about like maybe between 30 and 40 minutes of homework for the 1.2. It's not much. Trust me. You get started now, we have 7 minutes left. Yeah, so the ones at the end, obviously, you're just doing those 2 at the end. Yeah. And then 36, you're doing A and B only. And then 31 through 35. Again, the multiples refer to the ones over here. Okay? Do your best. If you really have trouble, if you really run If you work for more than like 40 minutes, just stop and then tell me, you'll be honest, okay? I'm telling you, though, it's not going to take you more than 40 minutes, so you probably won't want to be done anyway. It's not really a tough topic, this one. So one other thing I want to show you, to give you guys a heads up. Remember I said you're going to be doing these things called problem sets? In the beginning, I talked about problem sets, which are like mini projects that you're going to work on in groups. The first problem set is going to be due next Thursday, in 8 days. I already put it on Moodle. I'll show you what it looks like, though, so you have an idea. So, on Moodle, you're going to see, well, first of all, you'll see your homework for your notes for 1-3, and these were the notes for 1-4 through 1-6, if you want to print them. I'll put your homework up, obviously, for your section. And let's go to problem set 1. So under problem sets, you're going to see problem set 1. Oops. Okay? So this is going to be your problem set 1. There's problems from 1-1 all the way through 1-6. There's not a lot, like here there's only 4 of them. Here there's only a few in the even numbers. Then there's one problem here and a few here. It's not a ton, but this kind of a problem set, I'm going to collect all of this and grade it. Okay, I'm going to collect every one of these and grade it for you guys. And it's being counted as more than just a homework. So keep that in mind. This is like, for me, it's a way of seeing that you understand everything. It's your homework. Obviously, you guys see when I go around, I'm not checking every answer, right? I mean, you're not stupid. I'm checking for completion. I'm not going to insult your intelligence. But here, I will check all of your answers to make sure that you are clear with it. Now, what I'm going to allow you to do is work in pairs. Okay? And you only have to hit in one copy, not both. So if you put your names, both names at the top. Okay, but at the end of it, I want you to just sign we both did this. So it's not like one person doing it, the other person tacking their name on it. There are 11 of us in here. There could be one group of 3, and every other group is groups of 2. Does anybody want to work in a group of 3? Well, there are 3 people that would work in a group of 3. Okay, Edward? Anybody want to work with Edward in this group of 3? Figure it out amongst you. Who wants to work? Figure it out. Who wants to work in a group of 3? It's up to you.